The Earth's magnetic field, often described as an invisible force that shields our planet from the continuous bombardment of solar radiation and cosmic particles, is undergoing a series of unusual changes that have alarmed researchers across multiple scientific disciplines, prompting renewed investigation into what these anomalies mean for the future stability of Earth's protective systems. For billions of years, the magnetic field has served as a planetary guardian, generated deep within the Earth's outer core where molten iron moves in complex, turbulent patterns that create a vast geomagnetic engine known as the geodynamo. Under normal conditions, this field behaves predictably, shifting slightly over centuries and occasionally reversing polarity over extremely long geological timescales, but recent observations show that the system is acting in ways that do not align with the slow and gradual pattern expected from Earth's magnetic history. One of the most concerning elements is the steady weakening of the field measured over the past 150 years, with the rate of decline accelerating in the last 2 decades. Scientists estimate that the global magnetic field has weakened by nearly 10% in that period, a surprisingly fast shift in geophysical terms. The weakening is not uniform. Instead, a particularly strange region known as the South Atlantic Anomaly has captured scientific attention due to its unusually low magnetic intensity, creating a dip in the shield that allows harmful solar radiation to penetrate closer to Earth's surface. This anomaly affects satellites, spacecraft, and even the International Space Station, forcing them to take protective measures when passing through the region. Instruments shut down, radiation spikes are recorded, and sensitive onboard systems become far more vulnerable to malfunction. This alone would make the anomaly significant, but recent expansions of the region and new secondary weak spots emerging to its east suggest that the magnetic field in this area is evolving more rapidly than scientists predicted. At the same time, another surprising phenomenon has been detected: the magnetic North Pole, which historically drifts slowly across the Arctic over centuries, is now racing at unprecedented speeds, moving from northern Canada toward Siberia at almost 50 kilometers per year. This rapid drift has forced updates to global navigation models far earlier than planned, since aircraft, ships, GPS systems, and even smartphone compasses depend on accurate magnetic data for proper orientation. While magnetic pole drift is not a new phenomenon, Earth's poles have wandered and even reversed many times over geological history. The speed at which this is happening now is unusual and has sparked questions about whether it could signal the early stages of a geomagnetic reversal. Such reversals, though not catastrophic to life, can have significant consequences for human technology, as the protective strength of the magnetic field weakens during the transition, allowing more solar radiation to reach Earth's surface and atmosphere. If a reversal were to occur in our modern era of satellites, high-voltage power grids, and global communication networks, the effects could be far more disruptive than in any previous age. Increased radiation exposure could damage satellites, degrade communication signals, and shorten the lifespan of electronic systems in orbit. On the ground, a weakened magnetic field could leave power grids vulnerable to solar storms, potentially causing large-scale blackouts similar to the 1989 Quebec event, but on a far greater scale. Some researchers warn that the combination of a weakening field, the expanding South Atlantic Anomaly, and the rapid pole drift may indicate that the Earth's magnetic system is reorganizing itself, though it is still unclear whether this marks the beginning of a reversal or merely a temporary disturbance in the geodynamo. The complexity of Earth's core makes precise predictions extremely challenging. We cannot directly observe the molten outer core, so scientists rely on seismic waves, satellite measurements, and magnetic data collected over centuries to build models of how the magnetic field behaves. These models have improved dramatically with advancements in supercomputing and satellite missions like ESA's Swarm constellation, which continuously monitors Earth's magnetic behavior with high accuracy. The data reveals patterns that were previously invisible, showing that the magnetic field is far more dynamic and responsive to changes within the core than previously understood. Some theories suggest that patches of reversed or weakened magnetic flow deep in the core are responsible for the South Atlantic Anomaly, while others propose that shifting convection patterns in the molten iron are causing instability on the surface. Yet despite these advances, significant uncertainty remains. Scientists know that magnetic reversals occur on average every several 100,000 years, and the last major reversal, called the Bronze Machiyama reversal, happened about 780,000 years ago, meaning we are already overdue by historical standards. However, reversals are not clockwork events, and the magnetic field has entered periods of extreme weakening before without fully reversing. The real concern lies in the pace of change. For most of Earth's recorded magnetic history, shifts and drifts happen slowly, but today we are witnessing changes on a timescale that is fast enough to impact modern technology within a single human lifetime. Even though a magnetic reversal would not wipe out humanity or cause global extinction, the process could create a world highly vulnerable to solar activity. A strong solar flare striking Earth during a period of weakened magnetism could disrupt satellites, disable GPS networks, damage power grids, and interfere with aviation and maritime operations. Astronauts and high-altitude pilots could face increased radiation exposure, and regions near the anomaly could experience more frequent electronic disruptions. Despite these risks, scientists emphasize that panic is unnecessary. The magnetic field is still strong enough to protect life on Earth, and there is no indication of an imminent collapse. The real challenge lies in understanding the ongoing changes well enough to safeguard critical infrastructure. Governments and space agencies are increasingly aware of these risks and are investing in monitoring systems, shielding technologies, and predictive models to prepare for potential geomagnetic disturbances. Earth scientists stress that even though the magnetic field's behavior may appear alarming, it is ultimately a natural part of the planet's long-term evolution. The field has weakened and strengthened many times over geological history, and life has persisted through both reversals and major fluctuations. What makes today's situation exceptional is not the changes themselves, but the fact that they are unfolding during an era where human civilization depends heavily on technologies that are highly sensitive to magnetic disturbances. Our satellites enable global communication, weather forecasting, internet connectivity, and military operations. Our power grids sustain modern life, and our navigation systems underlie everything from personal smartphones to international air traffic. Therefore, even moderate disruptions in the magnetic field can ripple across society in ways that would have been inconsequential thousands of years ago. The scientific community is united in the belief that studying these anomalies is not simply an academic pursuit but a matter of global preparedness. Understanding how the magnetic field evolves can help engineers design more resilient technologies, governments create contingency plans for extreme solar events, and researchers improve models that predict future magnetic behavior. As new data continues to arrive from satellites, observatories, and deep Earth simulations, scientists hope to gain clearer insight into what is driving the rapid changes we are witnessing. Whether these trends signify an approaching reversal, a temporary instability, or a long-term shift in the geodynamo, one fact remains: Earth's magnetic field, the ancient shield that has protected life for billions of years, is behaving in ways that demand careful observation, scientific humility, and global attention.